the next speaker is Pano Maria, and he will talk about ontology matching.
Yes, thank you, Erwin. Yes, I think it's been like 10 years or something when we used to work at Cadastre, working on the first generation of the linked data platform together with Erwin. Thanks for having me. My name is Pano. Been working in data for about 15 years, and a lot in the semantic web and linked data community as well, but also in other Dutch government standardization initiatives like NLSBB, so that's like the controlled vocabularies standard. Sort of an application profile on SCOS, and also for MIM, the meta model for information modeling, which is a Dutch government standard for data modeling. And I've been involved in Shackle working group in the past, and currently as well in the RDF mapping language community group, where I'm a co-editor of a couple of the specifications. But today we're going to talk about ontology matching and a little bit about ModelDesk, because ModelDesk is a startup that me and Joost, who is also here, founded 2 years ago, where we're working on a problem that we've seen, and it's a problem that has to do with connecting data, metadata, and knowledge across organizations and across domains, and even within organizations. And the way we approach is we say, well, if you want to model knowledge, well, usually you need models, right? So and data, if you look at it, data always has a model, whether we express it or not. Data will always have a model, right? And in fact, each piece of data has multiple models, right? You have your physical structure of the data, your JSON schema, or your the way the data is structured physically. But you also always actually have a more conceptual, at least one more conceptual way of looking at the data. As in a sense, what does that data mean exactly, or what is the intent of that data in the business domain? So what we're building at ModelDesk is a platform to help organizations hopefully manage that better, to make those models more explicit, to collaborate on them, to maintain them. And one of the key things is that we want to do this in any modeling language. So it's a platform that is, in that sense, not tailored to a specific modeling language, but open for any modeling language. And the key is to be able to connect models with each other and with the underlying data, and hopefully use that to do interesting things with data. So ModelDesk is one of the key features that we have, of course, is that we want to model data. We want to visually model data. We have a lot of versioning and collaboration features that are based on a Git-like approach, and various ways to publish and share data. So that's a little bit about how we approach the modeling itself. But the key thing when you look at data, we think at least, is that there's the models that are going all the way up, right? So we have on the right-hand side, the physical and the logical and the conceptual layers. Those are the three sort of architectural levels that are quite standard, or you'd say well established in data modeling. So the physical, again, is your database schemas, is your JSON schemas. That's the structure of your data. The logical is usually a more normalized view of data in your organization. And then the conceptual is where you define the meaning of the concepts in your domain, right? So you define what is a customer, what is a transaction, what is a student, what is a course, what are the relationships between these concepts. But what we see is that these layers are usually not connected to one another, or not well connected to one another, if you look at current approaches. So one of the things that we want to achieve is we want to be able to connect these types of models, right? So to be able to connect your physical to your logical to your conceptual data from bottom up or top down doesn't really matter, and use those connections in actionable ways, right? To be able to drive data integration, to be able to drive business intelligence, data analytics, to be able to drive, to be able, in the end, to facilitate information and knowledge exchange by using these connections. So one example that I like to give is that if you look at data integration challenges, and I think you saw that in the presentation of Maarten as well, it's difficult, and it's also quite difficult because we are trying to do this always at the physical level. And this is, if you look at the current markets for data integration and analytics and data engineering, this is where most of the work happens, right? It's you have one data set and another data set, and we need to integrate them, and we're going to build some pipeline, we're going to do a lot of engineering to fix that problem, and we're going to integrate that. Then if you get another data set, we'll do it again and again and again and again, right? And we get a lot of point-to-point solutions. So the question we ask ourselves is, what would happen if we would do that one level higher, for example, right? So say we could do that at the logical level, where it becomes a little bit less of a point-to-point solution because we can do that at a higher level of abstraction, so it doesn't matter per se how the data is structured physically, if we can have the connection between our physical models and our logical models be actionable and be reusable in a way that we can generate the transformation at the physical level. So then what would happen if we do that one step up again, and what would happen if we could do that at the conceptual level, right? So that's the problem that we're thinking about and trying to solve as well. And this is where ontology matching sort of comes in. Because we're talking about mapping data and mapping concepts at the conceptual level when we talk about ontology mappings. Ontologies are, in a sense, conceptual models. They, I think, were popularized mostly by the semantic web movement, right? And OWL, the ontology web languages, is one of the more popular ways to express ontologies. And that's one of the sort of initiative that made it the most popular, I would say, that popularized the concept of ontology mappings, or model mappings, or model alignments, as we call them. So what do we need to create these mappings, right? Because models, the problem is models use different vocabularies, they use different structures, they use different standards. And one way that the ontology alignment movement approaches this is to say we can create a new model in between of the source and the target model that basically semantically will relate the concepts between the source and the target model, right? So you could see that as a sort of translation dictionary between different concepts. Now, ontology matching is actually the process of doing that in an automatic way. And this is something that as well started to become popular with the semantic web, where the goal was to create these huge databases of knowledge of the web and try to align them to each other. And for example, in the bioinformatics world, this is used a lot to do analysis on disease and to do the analysis on drugs and stuff like that. But basically what it is, it's a way to automatically discover equivalent concepts, to detect subset and overlapping relations, to do basically provide an initial mapping of similarity between concepts in different models. So how does it work, ontology matching, or how has it been researched in the last 20 years? Traditionally, it started with more lexical mapping, so more string-based approaches where you compare the names or strings, the names of things, names of entities. It then expanded to more structural approaches as well, right? You follow the hierarchy in the model and compare that. In the last couple of years, it's been more AI powered, right? So we have the notion of being able to apply machine learning to calculate similarity based on embeddings, or to use deep learning approaches where the train on known matches, right? So you train on existing models. And even more recently, of course, the language models have become more and more popular. And if you look at current research, there's a lot of combinations being used. So you have a combination of the lexical matching and the embeddings, and then some LLM plus RAG approach to sort of retrieve extra context and generate mappings. So what we did, we did a proof of concept with an organization that manages a lot of these types of alignments. They manage these alignments for several standards, and these are models that are usually these are OWL models, and they're usually quite big, so in around the thousands of concepts. And the problem that they had or have still is that the way that they manage these is in Excel. But they do that because they have some domain experts that are not very technical, right? They know what the models, what the concepts in the model mean, but they're not technical experts in the sense that they can make OWL-based alignments themselves, right? So they manage this in Excel, it's very error-prone and very difficult to manage. So we looked at together, like, okay, how could we provide an environment within ModelDesk in which you could manage this process in a more user-friendly way. So the process that we actually developed is that we could say, okay, you want to start to make an alignment. You can select your source and target models and determine which mapping candidates you want to map. Then you can define a sort of a working set, and the working set is basically just a subset of these candidates that you can organize by theme, because usually they have multiple experts that are an expert in a subsection of such a model. So the idea is that you can create these working sets and assign them to specific users that can then, as experts, start developing an alignment. Then when they make these alignments, they can also review this in the process with the actual technical experts that know about how to express these alignments more formally. When that is all done, we can release it. We can release the whole alignment as a model like we usually do, and have full change management processes running on that. And what we did, that was the first step. And then the second step of the project was, okay, can we use these ontology matching techniques to actually help these experts and give them some suggestions using the current possibilities with AI. So the approach that we introduced then in that process is to use a couple of these existing techniques. Right, so when we create this project, when we create such an alignment project, we can start computing already based on the ontologies, a set of vector embeddings. So this can happen in the background. And then once an expert starts to create an alignment, they are able to say, okay, please suggest for me a couple of matches, right, based on the embeddings and stuff like that. So you can ask the AI for suggestions. The first thing that the platform does is it does a similarity search on the embeddings, the vector database. that gives you a top, let's say, 10 answers or top 10 suggestions based on similarity. And the subsequent step could be to then give that and some extra context to an LLM for refinement. That's the idea, and then that could return suggestions, and you can use that in your alignment. So in a bit more detail, this is actually the process that we've currently implemented. So the top part is the pre-filtering, right, to give you those top candidates. And the second part is that LLM refinement, where we actually build a sort of a RAG-based approach. We build the context based on the ontologies, based on the selected items. We describe the task that needs to be done, right? So create this alignment. This is all the extra information, basically, and this is also what we want you to return and what the format should be. This is all the context that you give to the LLM. And then you execute the prompt and present that back to the user. So that's the basic idea of how these ontology alignments and how the ontology matching process is basically integrated into the process. So I can give a short demo of what that looks like. Refresh to be sure. So maybe so what you see here is an example. We have two ontologies, one on the left side, the source ontology basically, and one on the right side, which is the target ontology. And this ontology, we were looking for an example yesterday, so we found this one. This is some geolink-based ontology that apparently has to do with cruises and sampling, and this one has to do with water-based research. So there's some overlap, and the idea is that an expert user can click on the concepts on the left side, find some extra details as well. Can see what is the ancestor hierarchy, so the super subclasses. Has some initial context of what information there is. Can also hover to get more details about the documentation or about the definitions of properties. And the same on the right side, right? And usually an expert could do this by hand to say, well, I want to select participant with, let's just take something on this side, and we can build a match. So let's take another one. So what we added is this approach to say, well, let's add AI in there in a sort of unobtrusive way with these suggestions, right? So we can ask AI suggestions to find matches. And now, so what happens is the process that I explained just before. So it's going to first do this this vector search, then give the top responses, and that's going to send it to an LLM as a prompt, basically. It's taking long. Huh? Well, it's taking longer than normal. Let's draw it out again. So what is also quite nice with these LLM, what I think with the LLM-based approaches is, of course, that it's very good at creating a natural language. So one of the things that it does is then, there we find some matches, is it can also give you a sort of a rationale of explanation of why it chooses a certain match. So you get a couple of suggestions here for person. Apparently a person could be a subclass of a contribution, which is probably weird. But it's giving that as a 60% option. And then it says, well, a person could be a subclass of agent, and gives a whole explanation. And apparently it can find an even better match, which is then a person could be an equivalent class of an agent, which has agent type person, right? So this is basically, this is basically the best match as well if you look at the ontologies. And the cool thing is that because you can give it a specific format as well to follow, it can actually fill in exactly the correct OWL restriction format that it needs to do, and does that quite well. And then you can create a link, for example. And the idea is that you can then export these types of mappings. So you can export them as directly as Turtle, and apparently this is now the correct syntax for this mapping as well, right? So we have a person, which is the equivalent class of an agent, which is a restriction on property agent type with a value of person. So this is we're testing this out now currently with this organization, and it's being met with great enthusiasm. That's quite nice, and it's quite nice that we could use existing components from for specific research projects. So we could use, for example, the Al2Vec project to create embeddings based on ontologies, and use existing LLMs to do these types of extra filtering. So a couple of takeaways that we have from this project, and in general, like what we see is it would be it's very important for mappings to be reusable, not buried in code, and we think using ontology alignments is one of the ingredients for this. What we've seen in the project is if you work with domain experts, right, specifically for ontology alignments, they need tool assistance as well. They need help to express technically correct alignments, and AI can definitely help with this, right? They can it gives them a more conversational and a more human readable approach to working and explanation. What we also see is, AI should remain in the background. The humans should still decide, because what you see in applying these types of concepts more broadly is that it becomes difficult to distinguish if something is, properly reasoned about, right? So you get a sort of a collapse of explanation and exploration with the application of AI. And I'm wondering if you guys are noticing this as well, and if this is something that you have ideas about.
Okay.
That's it. Thank you.
I don't have to ask for questions.
Hello. Very nice talk. Thank you very much. It relates to stuff we do at University of Applied Sciences, of course. But one term in particular that actually was in two of your slides was context engineering.
Yeah.
Could you talk a bit more of the sort of items that are part of that? What do you engineer typically?
Yeah. So basically, what we provide as context for these alignment questions right now is information from the ontology itself. So if you have a certain class, what is the superclass? What is the superclass hierarchy until the top, and what are the direct subclasses? What are their definitions? Are there controlled vocabularies that are connected to the model? We pull in those as well that are that give enough extra context to the terminology and relations. Depending on how big the size is, we try to limit that as much as possible, because you see that the LLMs tend to work better with as small as possible a context. And we're currently also looking into adding extra documents if they are relevant to an alignment, but that sort of depends on the situation. So the idea is to have some of these options as well be configurable for each alignment by the users.
Okay.
Thank you.
Yep.
Did you consider using data lineage for this as well?
For sure. And you mean data lineage up until to the ontology, to the LLMs used, for example?
Yeah, for example, when you are on the physical layer,
Yep.
you have lineage, you have scanners, they discover certain relations between the data elements, but it's not always clear, right? Because the lineage cannot see in applications, for example,
Yeah.
right? You know,
Yeah.
this goes in, this goes out.
Okay.
But if you have ontology here and an ontology there, or conceptual data model,
Yeah.
then you see relations overlap, and then you can validate maybe certain parts of your lineage.
Right. Okay. We haven't looked at lineage in relation to ontology alignments in that sense, but we do have lineage baked into transformations from physical to logical to conceptual layers. So yeah, it would be quite interesting to see, can we expand that if you employ this ontology alignment approach as well as a sort of ingredient for these types of mappings. But we haven't done that yet, no.
Okay. Any other questions? No. Maybe did you already think about going one step further? Basically, you are creating your own trainings data with dismiss or approve. So maybe you can then also use AI to get your proposal or maybe the complete alignment in the end.
I don't know if you can get the complete alignment. I think that's quite a difficult task. But we are looking at what we are looking at is using the whole picture, right? To have alignment, the connections between models, the connection from physical to logical to conceptual. That's of course very interesting information to feed, be it as RAG or even as training data to specific AI applications, because it gives you the connection between how the business is modeled or how the domain is modeled towards the technical data, and even relations between different aspects.
Okay, thank you, and thank you very much, Pano.
Thanks.